Okay. Hello, everyone. I'm Renee Yager. I'm the Director of Marketing at EPC, and welcome to today's webinar, projecting a lifetime of GaN FETs and ICs in space applications. This is the third of our four-part summer series, which is running bi-weekly through the end of this month and focusing on GaN reliability in real-world applications. If you missed the first two installments, which were on solar and DC-DC, those replays are available on the website at epc-co.com. Remember that you can earn reward points for registering, attending, and engaging, and be entered into a raffle to win a $2,500 Amazon gift card. The details of the awards program are available on the website as well. Before we get started, just a few housekeeping items. You will have the opportunity to submit text questions to the panel by typing your questions into the Q&A function at the bottom of your screen. You can send in your questions at any time. We'll collect these and address them during the Q&A session at the end of today's presentation. If you are participating in the rewards program, make sure you identify yourself when you're asking questions so we know who to put those awards to. So now I'd like to introduce our speaker today. Dr. Shankye Zhang is Vice President of Product Reliability at EPC, where he leads the conduction of failure analysis for all GaN transistors and ICs. Prior to joining EPC, he worked as Senior Failure Analysis Engineer on RF MEMS devices in the mobile industry. He earned his PhD degree in Materials Science and Engineering from Arizona State University, investigating low-loss dielectrics for cellular and advanced computing applications. He is the author and co-author of more than 20 technical papers, and he is also a committee member and internal liaison for JEDEC's JC70 Wide Bandgap Power Electronic Conversion Semiconductors Committee. Now today, because we're talking about space, we're going to share information about the Rad-Hard EPC 7000 series that is available from EPC. And we're also going to be sharing information about the Rad-Hard package devices, which are available from EPC Space. Shankye, thank you for joining us today.
Okay, thank you. So today in this presentation, we will answer the question, why GaN power devices are the best choice for power conversion applications in space-based systems. GaN devices offer dramatically improved performance over the aging Rad-Hard silicon MOSFET, enabling a new generation of power converters in space, operating at higher frequencies, higher efficiencies, and a greater power densities than ever before. So first, we will explain why eGaN devices exhibit such superior radiation tolerance compared with silicon MOSFET. Next, we will explore some of the failure mechanisms in GaN and how they impact radiation performance. Next, we will then show the superior electrical performance of GaN transistors compared with the most popular Rad-Hard silicon MOSFET. And lastly, we will discuss some spaceborne systems where GaN is enabling higher radiation and system performance compared with silicon solutions. There are several types of radiation experienced by semiconductors in space. Three of the primary types of radiations are gamma radiation, neutron radiation, and heavy ion bombardment. So an energetic particle can cause damage to a semiconductor in three primary ways. First, it can cause traps in non-conducting layers under gamma radiation. Second, it can cause physical damage to the crystal, also called displacement damage, which is resulting from neutron radiation, typically. Next, under heavy ion radiation, it can generate a cloud of electron-hole pairs that could cause the device to momentarily short, possibly burn out in the process. Because of the device construction and the intrinsic materials property of GaN, energetic particles cannot generate momentary short circuit conditions in GaN. Gamma radiation. So gamma radiation consists of high energy photons that interact with electrons. Here is a cross section of typical silicon MOSFET. It's a vertical device with the source and gate on top surface, and the drain on the bottom surface. The gate electrode is separated from the channel region by a thin silicon dioxide layer, as you can see that right here. The gamma radiation knocks off an electron out of the silicon dioxide layer, leaving behind the positive charged traps, as shown right here. These positive charges reduce the threshold voltage of the device until the transistor goes from normally off or enhancement mode to normally on or depletion mode. At this point, the system will need a negative gate bias to turn off the device. Typical rating for red hot silicon MOSFET range from 100 kilorad to 300 kilorad. In some cases, devices can be made up to 1 megarad, but they tend to be very expensive. Compared with enhancement mode gallium nitride devices, they are built very differently from a silicon MOSFET. First, all three terminals, gate, source, and drain, are located on top surface. The gate is separated from the underlying channel by an aluminum gallium nitride layer, showing right here. This layer does not accumulate charges when subject to gamma radiation. Therefore, GaN intrinsically is less susceptible to gamma radiation. To demonstrate its performance, we took our 100-volt family of eGaN transistors to 500 kilorad of gamma radiation. We measured leakage current from drain to source, gate to source, as well as the threshold voltage and the on resistance at various checkpoints along the way, confirming that there are no significant changes in device performance. We have since taken devices out to 50 megarads, confirming that eGaN devices will not be the first part to fail due to gamma radiation in space systems. Neutron radiation. The primary failure mechanism for devices under neutron bombardment is displacement damage. High energetic incident neutron particles scatter off atoms in the crystal lattice and leave behind lattice defect, which manifested as lattice vacancies and interstitials. In MOSFET, the RDS zone is the most influenced parameter by displacement damage because the bulk resistance that suffered the most from displacement damage at approximately 1 times e to the 14 neutron affluence. This new piece of data of 300-volt gallium nitride devices show that higher neutron exposure up to 4E15 fluence with minimum or even no degradation in all 4 parameters measured. The need for reliable devices at those high exposure could be seen in future applications, such as fusion systems for nuclear for nuclear power spacecraft being developed for mission to the Mars and beyond. Here we are showing the impact of neutron radiation at doses up to 4 times 10 to the 15 particles per square centimeter fluence. The impact of neutron on the GaN crystal and the entire device performance is very minimal for 200-volt GaN devices. And lastly, here shows the neutron radiation test result of 100-volt GaN devices, also at doses up to 4 times 10 to the 15 per square centimeter. The impact of neutron on 100-volt GaN devices is very minimum too, as you can see in the result here. The reason for GaN's superior performance under neutron radiation is because GaN has a much higher displacement threshold energy compared with silicon, as shown in this graph, where you can see how much higher the displacement energy of GaN is compared with silicon, highlighted. Next, we are going to discuss single event effects. So single event effect, or SEE, are caused by heavy ion generated by the impact of galactic cosmic rays, solar particles, or some other energetic particle in space. This can be simulated by using a cyclotron to create beams of different ions. Two of the most common ions used in the lab to evaluate radiation tolerance of electronic components are xenon with a linear energy transfer, or LET, about 50 MeV square centimeter per milligram, and gold with a LET of about 85 MeV square centimeter per milligram. In silicon MOSFET, there are two primary failure mechanisms identified, which are caused by these heavy ions. One being single event gate rupture, and then the next one, the other one is single event burnout. Single event gate rupture is caused by the energetic atoms causing such a high transient electric field across the gate oxide, where the gate oxide ruptures. So, and the second major failure mode is single event burnout. It's caused by when the energetic particle transfers the drift region of the device, where there are relatively high electric field. The energetic particle loses its energy while generating a large number of electron hole pairs. These electron hole pairs cause the device to momentarily short circuit between the drain and source. This short circuit can either destroy the device, which is called single event burnout, or the device can survive, but it appears as a momentary short circuit that can cause damage to other components in the system. The latter case is called single event upset. Since EGaN devices do not have a gate oxide, so they are not prone to single event gate rupture. Shown in this graph is the primary wear-out mechanism for GaN devices under heavy ion bombardment. The conditions are about the maximum operating condition possible, with an 85 LET of gold atoms bombarding the device, bias at 200 volt, the maximum drain rated voltage of the datasheet limit. On this plot, the vertical axis is the drain leakage of the device, while the horizontal axis is the number of heavy ions absorbed by the device per square centimeter. The plot shows that the drain to source leakage current for 3 representative EPC 7 series 200 volt rated GaN transistors is the drain source leakage increased slightly, as you can see in the plot, as the heavy ion increases, but the leakage is still well below the datasheet limit. Please note that the gate leakage does not go up during the heavy ion radiation. So now let's take a look at the superior electrical performance of GaN devices. So here is the EPC's 200 volt GaN devices. As you can see that right here, the 200 volt GaN devices is about 10 times smaller, 10 times lighter, and at least 40 times faster. So next, EPC space 100 volt EGaN devices is about 25 times better in terms of hard switching figure merit, and 3.5x better in soft switching figure merit. And also, they are significantly better in terms of radiation level, as highlighted right here. Lastly, let's take a look of our EPC's 40 volt GaN devices, EPC 7019, which is smaller and 20 times better in figure merit and more red hard and lower cost. So now we have examined the superior irradiation and electrical performance of GaN devices. Now let's take a look at some of the applications where these products can be used. So power supplies using harsh environment, such as space, high altitude flight, or high reliability military space applications, must be resistant to damage or malfunction caused by ionizing radiation. Red hard GaN enables power converters operating at a higher efficiency, higher frequency, and greater power density for micro, LEO, and GEO satellites, along with deep space and outer space explorations. Here is an example of space-qualified DC-DC converter for satellite power from our friends at VPT using red-hot GaN FET. The peak efficiency reaches 96% compared to typical MOSFET solution, which typically do not exceed 90% range. Another application in space for GaN is lidar. Lidar systems provide the eyes for autonomous navigation and docking for rendezvous missions and robotics using space. The shorter laser beam pulse, the higher resolution of the lidar images. So GaN devices provide this needed speed and increase efficiency and shrink the die size for lidar. Next, reaction wheels are a critical component for satellites as it enables them to stay oriented and reposition while in orbit. The reaction wheel operates by controlling the rotational speed of the electric motor attached to the flywheel. Red-hot GaN power devices provide a smaller die size, lightweight, and the precision control that DC motors require and can withstand the harsh environment. So an ion thruster is a form of electric drive used for in-mission spacecraft propulsion with uses such as orientation and positioning of satellites and interplanetary propulsions of low-mass robotic vehicles. Red-hot GaN enables smaller, lighter, and more efficient power supply to these systems, increasing the power delivery. To summarize, GaN devices have significantly different failure mechanisms compared to silicon MOSFET. When exposed to various forms of radiation, GaN devices are more rugged than red-hot MOSFET. The electrical performance of GaN devices is many times superior to the aging silicon MOSFET. And lastly, GaN devices are the most efficient, smallest, and most reliable solution for spaceborne systems, including DC-DC converters, lidar systems, motor drives, and ion thrusters. Thank you. That's conclude today's webinar.
Thank you, Shanky. Okay, so now we're going to start answering the questions submitted during today's presentation. Also on the panel, we have Brian Miller, who is our field applications engineer for the Americas, and Belle Lazar, who is CEO of EPC Space and COO of EPC. As a reminder, you can still submit questions by typing them into the Q&A feature at the bottom of the screen. So we will get to our first question, which was, what was the switching frequency in slide 11 for neutron response?
Neutron, I think it's that's a DC measurement. There's no switching frequency in the data we presented.
Okay. Does the SEE effect depend on the operating temperature? For example, if you operate the GaN device at lower current and voltage stress, can you avoid the effects of SEE?
First, SEE in GaN, we don't have the typical definition of SEE. So what we observed and also what we developed for is we saw a small increase in the drain leakage, and we designed for that. So that's the mechanism we identify in this as heavy ion radiation. So yeah, I think that's kind of answer the question.
Okay. When will there be an update on the qualification testing of the EPC 7014?
I can answer that. The Group E testing completes on August 22nd, and we'll have the report finalized August 30th.
Great. Has any radiation testing been performed on some of the GaN offerings that the IC offerings basically? So devices with drivers built in like the EPC 231, EPC 2152.
Bill, can you?
Yeah, we haven't tested the 2.3 or package part series, but we have tested the 2152 series. We do have actually an equivalent guaranteed radiation hardened device, and it's EPC 7011, and the single event performance was excellent. We are selling the device in engineering units. We haven't qualified it yet, but it performed very well under single event.
Thank you. Let me see. Okay, in relation to your earlier slide for GaN being more resistant to displacement damage, does EPC Space need to make any changes to your commercial GaN devices to make it rad hard?
So, Sheki, I'll take this question. You can add more. So we have EPC Corp and through its division EPC Space, we have EPC Corp has developed a radiation hardened device by design, and it's EPC 7 series. We provide them both in chip scale form and a package form through EPC Space. The other devices are not guaranteed, but they could pass. But we did have to make a change to several changes actually to make them red hard by design. Yes.
Could you please elaborate on what parts of a lidar system can be replaced with your GaN devices? That might be a Brian question.
What parts in a lidar system?
Yeah,
The,
elaborate on what parts of a lidar system can be replaced with GaN.
Yeah, two parts. Well, the transistor itself that would turn on and pulse a laser. And the second part would be the gate driver. EPC has some brand new parts that integrate a gate driver along with the power FET. So those two parts together could be replaced. Going further into a higher power system, some people have used very small EPC GaN FETs as a gate driver, kind of a discrete gate driver for a bigger FET. So that's possible also.
This might also be for you. What voltage rated GaN devices are required for ion thrusters?
What was the question again?
What voltage rated GaN devices are required for ion thrusters? We list that as one of the potential applications.
Oh yeah, I mean, it depends. We've got some customers that are using our GaN devices, which is a module, but it really depends on your circuit design. There's no specific voltage.
Okay. What is the difference between rad hard product GaN and commercial product GaN?
So the red hard product GaN is designed to withstand single event under, so we actually sell the EPC 7, which is red hard by design. The others are not designed specifically for radiation hardened, but some of them might pass. So there is a difference in design, and the EPC 7 series is guaranteed for radiation performance.
Which condition during SEE testing is considered to be worse? VDS max at VGS equals 0 volts or VGS equals -4 volts?
Shenke question.
Okay. So in our radiation testing, we actually did -4 volt on the gate. But in reality, from a failure mechanism point of view, we don't see we don't really see a significant difference or noticeable difference when you apply because the -4 volt is a heritage condition from silicon MOSFET. But for GaN, I don't from our experience does not really matter that much. And also from our testing result, we don't see a gate leakage current change during the single event testing.
Did you perform SEE tests under dynamic conditions?
Well, I'm not aware of any. under, so Bell, are you?
I don't think so. I don't think so, but we can take that and circle back, but I don't think so.
Have you done any testing about the effects of the solar flare?
I mean,
Bell,
solar
okay.
flare as part of it could be a heavy ion bombardment in space. So we actually guarantee our EPC 7 series to perform under heavy ion bombardment up to 85 net. So I would say yes, it can actually withstand.
Can we avoid I guess that's gate drain, short circuit, and thereby burnout?
Gate drain, let me think. I think we'll probably need more clarification on this question. Gate drain, yeah.
Okay. Can you comment on normal versus angular testing for EPC GaN devices? Which condition is worse?
Okay, this is the question from the angle from a single event.
Oh.
Yeah.
Bell, do you have any information?
We do have data. We do have data actually, and we've tested them both at 90 degrees and an angle. And I think the 90 degrees we'll get with our CTO Max, who's performed the test, but I think the 90 degrees is worse. But we've done testing at various angles, and we test them at the worst angle.
How many samples have you tested for SEE testing, and is the performance repetitive?
We have, we actually, between EPC, C and EPC space, we test every wafer that we run for production or R&D gets single event tested. We go about 5 times, maybe sometimes 6 times a year at Texas A&M. And so we've done a lot of testing in the last 6-7 years. But every wafer is tested for single event. As far as repeatability, for all the production released products, we have a huge level of repeatability. We don't really have a lot of variation. But once we design a product for single event, the results are very consistent. But we do test every wafer before we every wafer that's shipped, we test it for single event.
What's the highest levels instantaneous TID gamma radiation, which one of your GaN devices has been tested for? I'm looking at nuclear applications for this technology.
Well, okay, so we actually, when we test, we don't test specifically for any nuclear applications, but we can tell you what we test for. We test to meet 19500 requirement, which is 1 megarad. But I know some of our customers and users have tested up to 40 megarads with no issues.
Okay. How do you protect the devices against cosmic ray?
So cosmic ray typically consists of gamma radiation, neutron radiation. If ever, I think from my study and understanding, probably neutron radiation is more harmful among the cosmic rays. So we have tested our device at doses up to 4 times 10 to the 15 fluence. So we see very minimum device degradation. We have multiple checkpoints along the way. So, and the reason is that GaN has much higher displacement threshold energy than silicon. So basically, GaN is more intrinsically robust against the cosmic ray. So we don't really need to. That's kind of, so basically compared to silicon MOSFET, GaN is much significantly superior against cosmic ray radiation.
Okay. How many samples can be tested at a time using this technology?
So I had a question on single event.
Maybe.
So yeah, I mean, we don't disclose our test setup, but we test typically like under 10, and we test each wafer.
Okay. This may be for Brian. Can you explain in more detail about how GaN improves lidar?
Yeah, for LiDAR, you want a very quick, high power pulse of laser to bounce off of something, take measurements in 3 dimensions. The GaN FETs switch very quickly, and also, especially the chip scale ones, have very low inductance. So you can have a very quick, not just transistor switch, but the whole loop, power loop, to really pulse a laser, I mean, sometimes down to, say, 1 or 2 nanoseconds at very high current with some good voltage behind it. That's a real big advantage in the LiDAR, getting the best, longest range and the best resolution.
If the gate drain is shorted, the GaN will go into linear mode. Is the GaN then robust to gate drain short circuit during radiation?
So it's diode, basically. That's a good question. So Brian, do you have any insight on that question? When you were testing?
I haven't seen that type of thing, a gate to drain. I mean, you can do it, but it hasn't really come up as an issue. So I assume it seems more like a destructive thing. I mean, gate to source, gate to drain. No, I'm sorry, I don't know.
You'll definitely know the answer to this. What is the best resource for finding GaN equivalents to MOSFETs?
Oh, our cross-reference. Yeah, Renee is smiling. You go to the homepage of epc-co.com, and there's a search box. And there's 2 options for the search box. So you can just type in the part number of your favorite until you press your former favorite silicon MOSFET, and then go to the cross-reference, and it'll bring up a selection of GaN FETs that can be, with a good, nice comparison of various parameters.
How is the performance of GaN against prompt dose effect, which would be mainly gamma radiation in a very short time range? And is there any result that can be shared?
Val, can you comment on the prompt?
Yeah, I
dose
mean,
effect?
we have done prompt dose testing with the data we have. We might not be able to share. We did it with under an NDA with some customers. But if you the person who asking question, if you could send me their information, we see if we can do an NDA and share some of that information with you.
See. Oh, let me go. Because some people sent them in. I had a couple. Do you do reliability screening testing, such as like burn-in, cycling, etc., before they go to production?
Well, as part of 19500, every lot goes through a full 19500 GaN-S equivalent screening, and including QCI before shipments. Now, before EPC Space gets the die at EPC Corp, we perform extensive reliability testing before we qualify the die. And once that's qualified, then it's released as we can start selling as what we call COTS. And then to sell Space, we go through a full package qualification. And the package qualification is based on GaN-S 19500. And once that's qualified, then the chip scale package part is also qualified. So we do a lot of reliability testing before production, during production, and after production is complete.
Have you tested your samples and then found that they're substantially beyond the current space radiation standards? I think that means perform better than the standard.
Yes.
Oh, that's succinct. This is a follow-on to the gate to drain short circuit. What would happen if you shoot a heavy ion along the 2-dag from source to drain?
Well, what the heavy ion, what we have learned is that that's the single event effect. Basically, we will see a slight increase in the drain leakage. So I don't think we can disclose too much on what's really responsible for the slight increase, because that's part of our development, critical development for GaN devices. But that's the data we shared today, which is the slight increase in drain source leakage. Gate leakage does not change.
Have you tested the performance of the GaN device if the PCB on which it is mounted is subjected to vibration and shock?
So I'll answer that. So we actually only test the units per 19500 in the QCI. We do shock and vibration, and they successfully pass. We don't mount them on PCBs and apply that. That actually our customers do that. But our devices meet 19500 shock and vibe spec.
So single event effects is comprised of several phenomena like SET, SEU, SEB. Are you testing your samples for all of these phenomena separately? Or can we classify the reliability data for these events separately?
Shenke?
Okay, so I think for the single event upset, so basically we have identified they don't do, because it's from the silicon world, they don't really apply. So what really apply the single event effect that we specifically test for every wafer, like what Bill just described. So that's what we are testing for our GaN devices.
So we test once and we get the results and we analyze and we see what type of failure we do have. Some failures do not apply to our GaN devices, but it's just once.
Have you performed any third-party standard testing, not in-house, of your rad-hard GaN FETs and ICs?
Third party, yes. Some of our customers have tested the devices both at single event and for TID. Yeah, the answer to the question is yes.
Okay. As you know, the validation and getting the certification for aerospace application is hard. How do you want to validate the results and get certification?
So as I mentioned earlier, every lot before it gets shipped goes through a full GNS equivalent space level processing, all the way from temp cycle all the way to the end, including through Group E, if you request the Group E. Obviously, ABC, AB on every lot, and ABCE, it depends on the qualification and the customer requirements. EPC Space has engaged with DLA, the Defense Logistics Agency, for a GNS certification. We do have our fab will be audited in October, and EPC Space will be audited in the next 6 months. We have submitted our slash sheets, and we are active members, the JEDEC, where we actually define the specs for GaN in space. So our goal is to get QPL product sometime early next year.
Deep space exploration missions may require very high quality power solar array using high voltage bus above 300 volts. Do you think GaN will benefit even for high voltage bus voltages, say higher than 300 volts? And do we plan to make high voltage GaN devices with ratings at 650 or higher?
Maybe GaN will benefit, but we don't have any plans for higher than 300 volt device at EPC Space.
But to add to that, there are some work going on with multi-level conversion, both from input and output. So we are working on that, and there's some significant advantages to that too, versus just single higher voltage GaN FETs. So I guess I just say watch this space. We'll might have some good solutions coming in the year or so.
To ensure reliability, do you do burn-in above rated bias for VGS and VDD before you ship to customers?
Shenke will answer the first question, and I'll answer the
Okay.
before we ship to the customers.
Okay.
Do you do burn-in above rated bias for VGS and VDD?
Bill, I think, are you going to
So
answer that
Shenke,
question?
why don't you describe the reliability, and I'll describe the production. So
Okay.
yeah, go ahead.
in reliability, we only test at the max rated voltage in reliability testing. So that's that's part of that's the qualification process. But in the previous two installments of our webinar, we try to understand the underlying failure mechanism responsible for gate and drain. That's where we developed the lifetime models. So the lifetime model probably still applies to GaN in general, but for very specific applications, that's something we probably need to have it's still based on the mission profile that you designing. So we need to have
for production purposes, we do by 9500, we do in screening 80% of the rated voltage, and in QCI, there's some subgroups that are 100% of the rated voltage.
Do your reliability models advocate testing above rated bias for burn-in?
Belle,
do you want to take that question? Or
I think it depends on what is our reliability. I don't think so, but we do test. We test to failure at our reliability group at APCC. But any production product is not tested above rated voltage. So you can look at our reliability report on apc-co.com website, and you can look at the data. But we have tested to failures.
Has any third party performed the whole 19500 qual flow, including life test and beyond it?
Say the question again.
Has any third party, I guess that could be customer too, performed the whole 19500 qual flow, including life test and beyond?
Maybe. We don't know.
For space applications in which linear mode operation is required, are silicon MOSFETs still superior or more rugged option compared to GaN?
I've heard from some people in the defense industry that GaN FETs do work very well in the linear mode. I can't say much, but the loop was working very well. There's other applications where they put just a small amount of current in the linear mode to prepare it to switch as fast as possible, and that works well also. So linear mode is supported with the GaN FETs. It seems like it works well from what we've heard.
What was the operating temperature for the graph in slide 18?
I believe this is an ambient temperature test.
It is actually room temperature, yeah. We don't really perform single event testing at elevated temperature or lower temperature, just room temperature.
Do you cover or test for high gamma, like 1 MGY plus GaN tolerance as well?
Is that the TID question? What was the question again?
It just says, do you cover high gamma, like 1 MGY plus tolerance as well?
That's Belle,
yeah, I mean, we actually, as I said, some of our partners and customers have tested our devices to like 40 megarads. We test every wafer lot to 1 megarad. So you get the results of any device that ships out of EPC space. You get what we call a TID report with it that shows the results up to 1 megarad. We don't test beyond 1 megarad for production.
When designing with wide bandgap devices like GaN, is it easy to control GaN devices as compared to IGBTs and MOSFETs?
Ryan, question.
Yeah, it's they are pretty easy to control, typically with a gate driver, a resistor, then the FET, and just by adjusting the value of the gate resistor, you can control the operation of it. There's no diodes or anything you need in the gate drive circuit. Also, negative voltage to turn off is not recommended for EPC GaN FETs and not needed, and there's no benefit. So that's makes it nice and simple for just a single 5 volts being off, 0 volts, 5 volts being on, 0 volts being off, control. So I'd say the control is pretty straightforward and easy.
Does a single event have any effect on the turn off, turn on delay of the device?
So switching parameters, I don't think so, but we can dig in. I'm not sure if you know, Shenki, but I'm pretty certain that it doesn't. Go ahead, Shenki, if you have any data.
Not that
Okay, so
on top of
we'll
my
have to
head,
get-
but yeah, we'll get back to you. Yeah.
Yeah, I'm pretty sure it doesn't, but we will confirm that with see if we've done any testing. So we'll have to get back on that question.
Are there any space qualified transistors at the very high frequency JF band?
I think the answer is a solid maybe.
Okay.
I think that's the range above the FM radio band, and I think I know the engineer who put in the question. So please contact us. The reason I say maybe is because it depends on the power level, exactly how you do the switching, the voltage, and so forth. So it's getting up there in frequency, especially for some of the larger GaN FETs. But if you have in mind a smaller amount of power, it could be willing to be discussed. And also the thermals, maybe it dissipates more. It is really very much application dependent, I think.
If somehow a device sustains SEE, is there any long-term effect on the performance of the device, such as on RDS on or switching loss?
So what we have learned on post SEE is this drain leakage increase. We tested other parameters post SEE up to the full fluence at 1E to the 7. So we don't really see any significant degradation in other performance. We can, but for sure we can go back and double check.
Yeah, no significant degradation. We actually, if you look at our spec, we're very close. I mean, it's actually spec'd out per the data sheet. Some customers want, they will accept higher leakage, but in general, there's no degradation.
Is there any concern to slow down the turn on of the GaN FET by adding a gate to source capacitor? This would be for a power distribution switch.
No, that's okay. It's becoming a bit more common, I think. I mean, a gate to source capacitor, yeah, you'll slow it down. I think more typical is increase the value of a gate resistor, but it's okay to add gate to source resistance to slow it down if you'd like.
Also to the prior question, Max is confirming your answer, Bell. No effect on turn on, turn off during TID or SEE.
Thank you, Max.
Thank you, Max. The IDSS degradation observed for SEE testing, is this permanent?
The answer is there's some effect, but it will recover. That's what we have learned. But still, even the quote unquote permanent effect is very, very small. Even this is the in situ is the worst, they will recover probably halfway, even less than that. So anyway, so the result is very minimal. You probably won't even detect it in circuit.
Okay. I think that is all the questions for today. If you have additional questions, you can feel free to send them in to us at info@epc-co.com. Within the next 24 to 48 hours, you'll receive a link to view a recording of the webinar. We'll also upload a copy of the slides as well. And I don't think you did it yet, right? You're presenting PCIM Asia next month, right, on reliability, or this month, Shanke?
That's right. That's right. Yeah, in a couple of weeks. Yeah.
Okay. And then lastly, just be sure and register to attend the last installment of the Summer of GaN series, which is on August 23rd, where we'll be covering using test to fail methodology to predict lifetime of FETs and ICs in motor drive applications. You can visit our website at epc-co.com for more information and to register. Thank you, Shankar. Thank you, panelists. Thank you, everybody, for joining. Have a great
Thank you.
day.
Thank you.
Right, bye.
Thank you. Bye.
Bye-bye.
Bye-bye.